This is Dr. Holt. In this video, I've created a system that has a mass with an initial velocity of 5 kilograms. Now this mass is going to slide down a frictionless surface until it comes to a location of B. Then it's going to encounter a frictional surface where the kinetic coefficient is 0.15. It's going to slide across a 10-meter surface. It's going to come across to C. It's going to slide back up this incline to D, and then it's going to come back across another frictional surface that has a coefficient kinetic friction of 0.25. It's going to keep going down this decline, or this surface here, until it hits a spring. It's going to compress the spring, and at that point the velocity is going to reach 0. Obviously it's going to spring back up, but we're only concerned about when it stops. And what I'm going to do along here is find all these different energy levels, and then at the end also find out what the spring compression is going to be. So I've established like my neutral axis. I call it my neutral axis, this location where I'm going to take all my gravitational potential from, and I'm going to work this problem, and hopefully by doing this you can kind of understand, or it will enhance your understanding of potential, gravitational potential, spring potential, kinetic energy, and work done by non-conservative forces. So I'll start out here. We're going to start out with A in relative to this position. We're going to find out what the potential energy is and the kinetic energy. So work down to here. To do this, what I like to do, and I follow this equation pretty much all the time, is my potential energy gravitation 1 plus my potential energy spring 1 plus my kinetic energy 1 plus my work done by non-conservative forces must equal to my potential energy gravitation 2 plus my potential energy spring 2 plus my kinetic energy 2. Now obviously if I'm going to be going from here to here, I have no spring potential whatsoever. My spring's sitting way over here. So I'll change this problem, or eliminate a lot of things. My spring potential here is going to go to 0. Now since I'm going from A to B, I'll go ahead and change these back to here, as these are all going to be my A positions, and these will all be my B positions here. And again, I could have done that in the beginning. I usually just put 1 and 2. Alright. So here we go. So my initial gravitational potential is going to be this mass times 9.8 meters per second squared times 12. So we'll come down here. We'll take 5 kilograms times 9.8 meters per second squared. Again, we multiply it by the h value, which is going to be 12. Plus, now we'll do kinetic energy. The kinetic energy is going to be 1/2 mv squared. I have a velocity of 2. So it's going to be 1/2 times my mass, which is 5 kilograms. Make that a little neater. Again, times my velocity, and my velocity is 2 meters a second. Let's square that. Now, between A and B, there's no work being done by non-conservative forces, in that there's no frictional force. This is a frictionless surface. So we can immediately let that go to 0 also. Alright, so now we have this value and this value. We'll run that real quick. So my gravitational potential is going to be 5 times 9.8 times my value of 12. That's going to give me 588 joules. Here, plus the value here, which is 0.5 times 5 times 2 squared. And that's going to give me 10 joules. So this is what I had in the beginning. We'll go back up here. We will check these right here. Excuse me. 588 joules and 10 joules. And that's where those two values there are going to come from. Now to find the gravitational potential to be. Since we're talking about this, we've established this is where we're taking all our gravitational potential. My gravitational potential here will be 0. So now I have no spring potential either, and I'm all talking about just kinetic energy here. I'll come back down here, let me put the joules in here. We set that equal to my kinetic energy, and again, if I add that, that's going to be equal to 598 joules. So I'll put that 598 joules. We will set that equal to 1/2 times my mass times my velocity squared. So I'll make this into 2.5 kilograms velocity squared. We'll divide by 2.5, so we take 598 divided by 2.5. We take the square root of that value right there, and that gives me a velocity of 15.467 meters per second. All right, and we come down to here and we say, what's our potential? Obviously, our potential here would be 0. What's our kinetic? The 598 joules that we got right here. And then, what is the velocity? Obviously, 15.47, exactly what we got here. All right. Now, this velocity is going to be constant until I get to B. Nothing has changed. There's no work being done by any non-conservative force as it comes down through here. So that velocity will be the same. So now we're going to go from here to here. The only thing that's going to change in my system is going to be the work done by non-conservative forces. So to find out what's taking place at C, we can come back down here and we know we're going to have 598 joules. Again, because we have a combination of, I'm sorry, not a combination, but we have just kinetic energy. So that's going to be our kinetic energy. So now we're going to do the work done by non-conservative force. Now the work done by non-conservative force is we need to find out what the normal force is, because we know that the frictional force is the normal force times the coefficient of friction. And I'll write that all down here. So my frictional force, K, a kinetic friction, again is going to equal to my normal force times the coefficient of kinetic friction. That's how you define the frictional force. I'm going to quickly draw a free body diagram of what's taking place of the 5 kilogram mass as it moves down to here. And I'll show you what I mean by that. I'll rotate this back into place. We're going to draw a free body diagram as this piece slides right along here. Let me move this out of the way. As this piece slides right along here, we're going to draw a free body diagram what's taking place. So I come down to here. That's going to be 5 times 9.8 going down. This will be my normal force going this way, and my frictional force is going back this way. So I define my gravitational force as 5 kilograms times 9.8 meters per second squared. When we do that, 5 times 9.8, that gives me a value of 49 newtons. This is going to be my normal force, and it's going to equal to 49 newtons because I have no other forces in the vertical direction. I go back up here again. We define the mu, the coefficient of kinetic friction is 0.15. We follow along exactly what we do here. We take our normal force, 49 newtons. We multiply that by 0.15, our coefficient of kinetic friction, and that's going to give me a value of 7.35 newtons. So this is our kinetic friction, 7.35 newtons. Now, if you notice here, the frictional force is pointing left. So as this object slides to the right, the work done by the non-conservative force is going to be negative because it's moving to the right, but the force is going back to the left. So the work being done is going to be the force times the distance. We're going to multiply that by 10 meters. So the work being done by non-conservative force is going to equal to negative 7.35 newtons times my 10 meters, and that's the distance it travels across here. And multiply that, that is going to give me negative 73.5 joules. So that's how much work is being done. So I'm going to come back over to here, move this up a little bit. I'll show you what I mean here. We're going to come back to this. We're going to change this back to the negative of negative 73.5 joules must equal to how much kinetic energy I have on the other side of the equation, because I'm obviously, as I get over to here and I start to go back up the ramp, I have no gravitational potential because I'm taking everything relative to this axis here. So all I'm going to have at C is going to be kinetic energy. So I can just set that equal to the kinetic energy, or equal to 1/2 times the mass times velocity squared at C if I want to find out what the velocity is. Now, if I take the 598 minus 73.5 joules, then my total energy at C has reached 524.5 joules. Again, that's all kinetic energy. I will set that here. We'll make that to 2.5 kilograms times VC squared. I will solve for VC. I take that value, 524.5. I will divide that by 2.5. I will square that value, or sorry, take the square root of that value. That'll give me a velocity at C is equal to 14.84 meters per second. So all this goes together here. Okay, so let's go up and check our values. So again, the work done by non-conservative forces here should it be like 73.5, which it is. What is the velocity at C? 14.48, exactly what I calculated right there. Oops, I wrote that wrong. I apologize. That's 14.48. I apologize for that. Math calculation. Look at my calculator right now. It says 14.48. I wrote it as 14.84. So that's 14.48. And again, what is the kinetic energy at that point? 524.5. And that's exactly what I got there. All right. So now we work our way up to D. To do D, as I move from here up to D, I'm going to be gaining potential energy, gravitational potential energy. If I'm gaining gravitational potential energy, I'm going to lose kinetic energy because there's no work done by any non-conservative forces as they move from C to D. So we'll come down here. We'll say I have 524 joules. That's how much energy I have. So my kinetic energy at C is 524.5 joules. Again, I can go ahead and write my equations. I know my potential energy. Gravitation at C is 0. We'll go ahead and cancel that out right now. Plus my kinetic energy at C, plus the work done by non-conservative force. And again, we know there's no work being done by any non-conservative force. There's no frictional force between C and D. We will make that also to be 0. There's no spring potential, so we can ignore that. So that must equal to the kinetic energy, actually it's your gravitational. Potential energy, gravitation at that point, which we're calling it as D, plus the kinetic energy I have at D. So I come back down here. I take 524.5 joules. I will set that equal to gravitational potential. Well, what's the difference in height? Well, it's 12 here and 10 here. So I've gone up 2. So my gravitational potential here would equal to the 5 kilograms, which is the mass. 5 kilograms times my 9.8 meters per second squared times the height, which is 2 meters, plus 1/2 the mass times v squared. Again, this value right here is nothing more than my kinetic energy. This is my kinetic energy here. This is my gravitational potential energy here. And again, I'll put that at D and put that at D. All right. So first thing to do, I'm going to find my gravitation. So we take 5 times 9.8 times 2. So my gravitation is 98 joules. So I'll rewrite this as 524.5 joules. Make that 5 a little neater. Is equal to 98 joules plus, again, do that again. That's going to be 1/2 times 5. That's 2.5 kilograms V at D squared. I will subtract 98 from that. 24.5 minus 98. And I get 426.5. So 426.5 joules is equal to 2.5 kilograms velocity at D squared. I will divide by 2.5. I will take the square root of that, and that gives me a velocity at D of 13.006 meters per second. All right, we'll go back, we'll check this. Again, this is the gravitational potential. And we'll see what we get here. And obviously, since I subtracted 98 from this, this is what my, right here, this is what my kinetic energy, it has to be at D also. Let's go back up here and check. And my gravitational potential at D, 98 joules. What's my kinetic energy? I got 426.5. I believe that's what I got down here. Yes, 426.5. And my velocity at D, I had 13.06. Let's check and see if I got here, and that's 13.06. All right, so we're moving right along. We're doing great so far. Now we want to find out what's going to take place between D and E. Now, your gravitational potential is going to decrease. I'm going down. Now, to find out what is the distance from D to E, that distance would be 20 meters times the sine of 47. That's going to give me the distance straight down here. Gravitational potential must be vertical. So I'm going to try to take a snapshot of this and see if I can get all this in here like that. And then I can hopefully drop this in down below. I don't have to keep going back and forth all the time, and make it a little bit easier for you guys to follow. Alright, so now to find the energy, let's find how much energy can be lost first. To do that, again, draw yourself a good free body diagram, because you cannot just do 5 times 9.8 times 0.25. You need to find the normal force. This is what I like to do with these type of problems, and this is a little unique the way I do them. I draw my force of gravity coming down like that. I draw this force normal to the surface, and I draw this force here like this. This is going to be my right angle here. This is going to be my force of gravity here. And that's going to be 5 times 9.8. That's going to give me my 49 newtons here. Get that out there. Sorry, my email's popping up. If this is 47 here, this angle here is going to be 47. You can prove that with geometry. I want to find this. This is what I'm interested in. That's going to be 49 newtons times the cosine of 47 degrees. And we're going to run that number real quick, and that's going to give me a value of 33.418 newtons. Now, when I draw my free body diagram, I draw like this. I draw this force coming down, which is normal to the surface here. I draw this force up here. I'll draw this force up here. And I'm draw this. This is the frictional force. So now this value again is going to be my 33.418 newtons. This is going to be my normal force of the surface pushing back up, and that's going to equal to 33.418 newtons. Now to find the frictional force, I always take normal times mu. So I'll multiply that by 0.25. My frictional force here is going to be 8.3544 newtons. Now this one here, which I'm going to just rewrite, which is this force right here, is just going to be nothing more than 49 newtons times the sine of 47 degrees. Now do not get confused. This is a this is a conservative force here. It is not going to do any work by non-conservative. It's not going to take energy away from the system. So you can ignore this. The only thing you're interested in is this F of K. It's going to do work in a negative way because it's a non-conservative force and is pushing in the opposite direction. So to find the energy loss, all I have to do is take this value times 20, because that's the application of the force all the way along. 20, I multiply that by 20, and my work done by non-conservative force, again, is going to be negative 8.3544 newtons times the distance of 20 meters. When I do that value, I will get minus 167.08. Let's make that 09 joules. So that's the work done by non-conservative forces between here and here. We'll go back up and we'll check that number real quick and see where if I got that correct. And I said the energy was 167.09, and there it is. So we're dead on right there. All right. So we're doing really well. We want to find out how to go from D to E. So we go back to our system. Remember, we have 524.5 joules to work with. So I'm going to rewrite the equations, and what we're going to have here is we're going to write the potential energy, gravitation at D, plus the kinetic energy at D, plus the work done by non-conservative forces must equal to the potential energy, gravitation at E, plus the kinetic energy at E. Now we know this value right here is the energy I had up here, which is 524.5. Because that's not going to change, so we put 524.5 joules. Now we have work being done by non-conservative. We know that's going to be minus 167.09 joules. Is going to equal to potential energy, gravitation. Now this is a little different, but we'll go up and look at the picture. We need to find out what the distance is down to E, right here, from this point. To do that, I'm going to take the 20, which we have right here, and multiply it by the sine of 47 degrees here. So if I take 20 times the sine of 47, that's 14.62. Now that would be coming off of D, 14.62. So I will subtract 2 because the difference between the 10 and 12 is 2. And that gives me a distance from B, the neutral axis here, the vertical distance back down to E is going to be 12.62, and it's going to be negative. So I come down to here, I put 5 kilograms times 9.8 meters per second squared. I will multiply that by negative 12.627 plus my kinetic energy I have at E. Alright, we'll do the math on the left side. I will take 524.5. I will subtract 167.09. That's going to give me a value of 357.41 joules is equal to, and this is the gravitational potential on the right, 5 times 9.8 times negative 12.627 gives me a value negative 618.726 roughly joules. So that's the gravitational potential I'm going to have at E. If we move this back to the other side, so I'll take 357 plus the 618. Do that real quick. That's going to give me, let me do it one more time. I messed that up. Sorry. Keyed it in wrong. 357.41 plus 618.7266. That gives me a value of 976.3, excuse me, 14, roughly 1366 joules of kinetic energy. Again, that's kinetic energy at E. So again, this is the kinetic energy I have at E. This is the gravitational potential. So let's go check that value there. The gravitational potential I have at E is going to be negative 618.73, which I believe I had. That is what I have, and 976.14. Again, go down and just check those numbers and exactly what I got. Now, if I want to find the velocity here, I just go back and use the kinetic energy of equation 1/2 times my mass, 5 kilograms, times the velocity at E squared. We'll set that equal to kinetic energy. So we'll take that value there, I'll multiply it by 2, I would divide it by 5, I would take the square root of that, and that's going to give me a velocity at E. Wish that thing would not pop up. The velocity at E of 19.76 meters per second. So that's the velocity we have at E. Again, let's just go up and verify. Okay. Oh yeah, we need to go up and verify this is correct. So I got 1.48 meters. Move it all the way up. Check the spring compression. It's 1.48 meters. Yep. So anyway, this is a very long problem. It's a very long video. But again, I started with this mass that was way up here. Grab this guy here. It was way up here. And again, I slid it all the way down through here. It's gone through two scenarios where it was work done by non-conservative force. It's gone back up. It's gone over. It's gone down. It's hit a spring. Again, it's very detailed, but I hope by going through this you understand how you can apply the conservation of energy and apply the application of work done by non-conservative forces to develop what the potential energy is using gravity. What the gravitational potential is and what the kinetic energy is, as well as how to apply spring compression. As always, I wish you guys the best of luck with your physics problems, and I will catch you next time.